Welcome back, junior engineers. I am absolutely thrilled to have you here for today's explainer. Today, we're going to explore what I think is one of the most fascinating phenomena in all of physics. We are looking at the absolute two-way street of electromagnetism. You see, electricity and magnetism, they aren't just two completely separate topics in a textbook. They are deeply, deeply connected forces that drive almost all of our modern technology. By the end of our time together, you're going to understand exactly how this relationship works, and better yet, you'll be ready to apply these exact concepts to design your very own communication system.
Here is our engineering roadmap for today. First, magnets and moving charges. 2, electromagnetic induction. 3, waves for communication. 4, your design challenge. And 5, a quick recap and transfer.
All right, Section 1, Magnets and Moving Charges.
Okay, let's dive into this. Back in the early 19th century, a Danish scientist named Hans Christian Ørsted made an incredible discovery. He noticed that a compass needle, which, is basically just a tiny magnet, deflected whenever it was brought near a wire carrying an electric current. This was huge. It was the very first major piece of evidence that moving electric charges actually create magnetic fields. But since magnetic fields are invisible, how do we picture them? Well, physicists use a really handy trick called the right-hand rule. Literally, just imagine you're grabbing a straight wire with your right hand. Step 1, point your right thumb in the direction the electric current is flowing. Step 2, allow your fingers to naturally curl around that imaginary wire. Step 3, the direction your fingers are pointing right now, that shows you the exact path of the magnetic field lines. They form these invisible, continuous, concentric circles right around the wire itself.
So, let's pause our pacing for a quick check just to see if you're visualizing this correctly. Imagine you have that straight wire, but now you completely reverse the flow of the electric current. What happens to the direction of the magnetic field? Think about what your right hand has to do for a second.
Do you have your answer? Yep, the magnetic field direction reverses too. And the reasoning here is entirely tied to the physical orientation of that right-hand rule we just talked about. If the current goes the opposite way, well, your thumb has to point the opposite way. And when you flip your hand upside down to do that, your fingers are naturally going to curl in the exact opposite direction. The magnetic field maps perfectly to the movement of those electrical charges.
Moving on to Section 2, Electromagnetic Induction.
Now, if nature is symmetrical, this brings up a massive, game-changing question. We know that electric currents can create magnetic fields, but is the reverse true on our two-way street? Like, can magnetic fields somehow create electric currents? So the crucial point is that they absolutely can, and it happens through a process called electromagnetic induction. Discovered by the brilliant Michael Faraday, this is simply the process of generating an electric current by moving a magnet relative to a coil of wire. And I really want you to notice the word moving there, because it is absolutely essential to making this work.
Let's break down Faraday's famous experiment to see exactly why that is. He found that if you take a bar magnet and move it towards a wire coil, boom, it induces an electric current right in that wire. If you pull the magnet away, it also induces a current, but this time in the completely opposite direction. But here is the real kicker. If you just hold the magnet completely motionless inside or near the coil, you get absolutely zero current, nothing. Motion and change are fundamentally required to make the magic happen.
To make this abstract idea a bit more intuitive, physicists talk about something called magnetic flux. Basically, that's just the amount of magnetic field passing through an area. Think of the wire loop as a sail on a boat and the changing magnetic field as the wind. To get the maximum push on your sail, it needs to be facing the wind directly, and obviously the wind actually has to be blowing. A stationary magnet is just like a completely still day on the lake. There's no wind, no push on the sail, and therefore no current whatsoever in your wire.
All right, time for our second pause check. Based on everything we just discussed about Faraday's setup and our sailboat analogy, how can you induce an electric current in a simple wire loop using just a basic bar magnet?
You have to move it. The answer is by actually moving the bar magnet through the wire loop. And this brilliantly illustrates the core mechanic of electromagnetic induction. An induced electromotive force, which is what creates our current, is directly proportional to the rate of change of the magnetic flux. A stationary magnet does not change the flux, so it literally does nothing. You absolutely need that changing magnetic wind to push those charges along.
Section 3, Waves for Communication.
Let's move to and see how this builds into something even bigger. We've seen how moving charges make magnetic fields and how changing magnetic fields make electric currents, but when you put these two ideas together dynamically, you get a phenomenally powerful tool for sending information. If you take an electric charge and make it oscillate, meaning you basically bounce it back and forth really rapidly like in an alternating current, it generates an electromagnetic wave. This wave consists of an electric field and a magnetic field that are perfectly perpendicular to each other. They're locked in this perpetual dance, traveling outward from the source. And the most amazing part, unlike water waves or sound waves that need a medium to travel through, these electromagnetic waves can travel right across completely empty space to carry a signal from one place to another.
Now, what's really interesting about this slide is how we actually use these waves to talk to each other in the real world. Think about your car radio. The information in an AM radio signal is transmitted by changing the amplitude or the physical height of the radio waves. Meanwhile, an FM radio signal transmits its information by changing the frequency, which is the number of waves that pass by every single second. Both systems use the exact same physics of electromagnetism, but they modulate or tweak totally different properties of the wave to carry their unique messages.
Which brings us to Section 4, the Design Challenge.
All right, junior engineers, we've covered the physics. Now it's time to actually apply this two-way street of electromagnetism to a real-world problem. Your mission is to build a fully functional communication device. But as engineers, you have strict constraints you gotta follow. First, your device must generate your initial signal using electromagnetic conduction. That means moving a magnet and a coil. Second, it must transmit that information through the air via a modulated electromagnetic wave. And finally, your receiver must catch and convert that invisible electromagnetic wave back into a readable format, like a specific sound or a blinking light pattern that humans can actually understand.
To help you target your designs, here's the rubric you'll be evaluated on. To reach that top-tier exemplary 3-point mark, your signal range needs to work completely across the classroom, not just up close on a desk. For your use of induction, you can't just randomly wiggle a magnet around. You need a clear mechanism that actively optimizes that magnetic flux change. Think back to our sail. How are you going to catch the absolute most wind? And for message clarity, a 3-point design won't just turn a light on and off randomly. It will successfully transmit complex data or clear intentional patterns.
Finally, Section 5, Recap and Transfer.
Before you head off to the lab to start sketching out your blueprints, let's take a quick moment to review the cognitive stack of physics concepts we've built today. Remember our two-way street. Moving electric currents create magnetic fields, which you can map out using the right-hand rule. Conversely, changing magnetic fields create electric currents through electromagnetic induction. But remember, motion is absolutely required. Finally, oscillating those charges creates propagating electromagnetic waves, which we can then modulate to send vital information across vast distances. This whole loop, it's literally the foundation of almost all modern communication technology.
I'm going to leave you with one final thought to discuss with your classmates before you begin building. We've talked a lot about radios and classroom communication devices, but this physics is everywhere. Think about going to a rock concert. How exactly does an electric guitar's pickup coil use the principles of electromagnetic induction to take the physical vibration of a metal guitar string and send a musical signal all the way over to the amplifier? Keep the two-way street in mind as you chew on that one, and good luck with your designs.